Our last speaker, Singleton.
Okay, so in contrast to the previous talk, I'm going to talk about something that really isn't very serious at all. It's basically a conclusive proof that theoretical physicists like myself don't know what they're talking about. So we have these two kind of very well-defined concepts in theoretical physics, black holes and information, which I'll tell you a bit about both of shortly. And when you throw them together, they don't play very nicely, and you end up with a paradox. So I'll take you through how that works and then sort of describe how we don't know how to resolve it. Okay, so black holes first. And you've probably heard the kind of standard spiel about black holes, which is that they are a region of space from which nothing can escape. And it doesn't matter how fast you travel, it doesn't matter how big an engine you've got, how clever a trick you try, you are not going to get out. And there are sort of two characteristic features that are important here. The first one is this thing called the event horizon, which is basically the threshold. So once you step over this line, that's it, you are done for. And the really important thing about the event horizon is that once you're in, you can't send any signals out. Because if you could send signals out, you could probably send yourself out as well. That doesn't work. So these things form by collapsing very, very, very large amounts of matter. So say 3 times the mass of the sun. There are plenty of these things in the universe, so they do actually exist, we think. You collapse this stuff under its own gravity, and eventually it collapses down so far that it's essentially just a single mass at a point, so it's infinitely dense, and there's infinitely strong gravity at this point called the singularity. And once you've fallen inside the event horizon, you are doomed eventually to hit the singularity, and it's going to be seriously unpleasant for you because this infinitely strong gravity is going to tear you to pieces. So just to give you an idea of the kind of ridiculous scale we're talking about here, if I take a grain of flour, that's roughly the smallest thing that a human eye can actually resolve, and give it the same density as a black hole, it's going to weigh about the same as the moon. Okay, so on this slide we have an artist's impression of a black hole. It's kind of pretty. It would be even prettier if this projector could actually show red, but never mind. So on the next slide we have a scientist's impression. And this is not so pretty, but it's got a lot more information in it. So let me take you through what's actually going on here. So we have time running up the page. So at the bottom, early times, late times at the top. Space runs side to side, and the important feature is the angle that the light rays move at. They're going to move at 45 degrees. And because relativity tells us nothing can move faster than light, everything has to move up at least as much as it goes sideways. So any actual particle will follow a trajectory that mostly goes up on the page. So what have we actually got here? In this large white region, this is where you're safe. You are far from the black hole. You can kind of sit there externally observing it, and no particularly bad, malicious things will happen to you. So at early times, so towards the bottom of the page, we've got this kind of ball of collapsing stuff, this grey shaded region. So this is our dead star or whatever, collapsing under its own gravity. And eventually, it crosses this, what should be orange line, which is the event horizon. And when the surface of the star crosses the event horizon, you form a black hole. And anyone out here is going to be unaware that there ever was a star there in the first place. Because the surface of the star, that's now inside the event horizon, if it tries to send out a signal, well, it goes at 45 degrees, the same as the horizon. It's just going to hit this line up here, which is the singularity. So this is the really, really crucial point of this slide, is that once anything is inside this region, it cannot emit any signals that can be observed by anyone out here. That's the key thing. Okay, so another important feature of black holes is that they all look rather similar. And that's a more meaningful statement than just saying that they're all black. So if we look sort of late on, well after this star has collapsed and formed a black hole, so at this shaded region up here, and zoom in on it, we get this picture. So if someone comes along much later, and tries to observe, like I said before, they're completely oblivious to the fact that the star was ever here, because the signals are all trapped in this region. So from their point of view, all they can learn about is obtained just by looking at the black hole from the outside. That's not very much. They can learn exactly 3 numbers. They can learn how heavy this black hole is, they can learn how much electrical charge it's got, and they can learn how fast it's spinning. So from their point of view, all prior knowledge of the collapsing object has basically disappeared. Okay, and that's going to come into profound conflict with our other concept, information. So, information, roughly speaking, is just a list of numbers that tells you everything about the physical state of a system. So, for example, the stuff in this room is made up of a bunch of particles, and if I tell you where those particles are, how fast they're moving, what the forces between them are, and so on, I've exactly characterized the system. However, quantum physics, one of the various things you're going to have to take on faith about quantum physics, is that tells us that the length of this list can't change. So if I need 1,000 numbers, say, to specify everything in this room at time 0, and I wait a minute, I will still need 1,000 numbers. The actual values of those numbers can change, but the length of the list will always be the same. The outcome of this is that information can never be lost. And it's really, really, really hard to overemphasize how strong a statement that is. So to try and overemphasize it, I've drawn a silly picture. So, the claim is that if the worst possible scenario were to occur, and all of human knowledge were to get engulfed in a horrific fireball and burned to a crisp, if you were to very carefully collect all of the ash and light and so on given off by this fireball, piece it back together carefully enough, you could reproduce the entirety of human knowledge, because you can never lose information. And some smart-ass physicist is bound to try and tell you that when you're watching Shakespeare burn. Okay, so this is already looking a little bit paradoxical, because if you recall, we started with a star. That's a really, really huge thing. It needs a huge amount of information to describe it. There are billions upon billions of particles in the thing. And then it collapsed to form a black hole, which I just told you we needed 3 numbers to describe. And 3 is much, much smaller than billions and billions, and so we appear to have lost information. So that looks a bit like a paradox. But just now it's not. And the reason it's not is because if you were desperate and insane enough, if you had, accidentally dropped the one thing in the world you absolutely could not live without into this black hole, you could jump in and you would be able to be reunited with your treasured possession. And I'm sure that this would be a great comfort to you as you were falling to your inevitable death at the hands of the singularity. So far, we do not have a paradox. But we can turn it into one by directly contradicting something I said earlier. And that is that if it turns out, if you treat black holes quantum mechanically, they are in fact not black at all. So, so one of the spookiest of the spooky predictions of quantum mechanics is that pairs of particles can spontaneously appear and disappear. Not only that, but they actually do this around us all the time. So just say that again. Pairs of particles can pop into existence out of nowhere and then disappear again. And this happens constantly. And usually this sort of happens so quickly that the universe doesn't notice it happening and life continues as normal. But the question we can now ask is what happens if we produce one of these pairs either side of an event horizon? So here I've got one particle inside the black hole, one particle outside. Okay, well, we learned earlier that the particle on the inside, that's doomed, because it's inside a black hole. It's going to have to hit the singularity. However, the particle on the outside can escape and be observed by some annoying person sitting over here trying to look for it. Okay, so from the point of view of this person, he sees this particle, but he's completely oblivious to the fact that this one ever existed. Okay? So he thinks that the black hole is radiating. This effect was originally observed by Stephen Hawking, by the way, and is the main physics reason why he's famous. So, the black hole is radiating, and if the thing is radiating, it's going to lose mass because it's giving off stuff. So, you run this process forwards, and eventually it's going to lose all of its mass. It's going to disappear completely. So, just to run the logic again, we started with a dead star, which we needed loads of information to describe. It collapsed to a black hole. The black hole then radiated away, disappeared, and left us with just this cloud of radiation. And this is where the paradox comes from, because this radiation contains no information about the black hole besides those three numbers that we needed to describe it earlier. So it knows about the mass, about the electric charge, and about the spin of the black hole, but nothing about anything that actually fell in to form it in the first place. So, we started off with loads of information in a star. We've ended up with 3 numbers worth of information. This is a paradox. And it's a thorny one. It's got physicists completely stumped. This was pointed out in the 70s, and we still don't know how to resolve it. So I'm going to go through a few of the potential resolutions in sort of order of increasing bonkersness. So this is the first one. So, people have tried to argue that perhaps if you do the calculation leading to Hawking radiation a bit more carefully, you might find some subtle correlations between the radiation released by the black hole when it evaporates and the stuff that fell in the first place. And it was believed for 30, 40 years that this would be true if only we could do the calculations and that this would resolve the paradox. Unfortunately, a couple of years ago, this was proved to be completely bogus. Doesn't help you at all. So we started coming up with crazier solutions. So the next one is to claim that there's no event horizon. If there's no event horizon, then there's also no paradox, because you can send signals out of the black hole. The argument for Hawking radiation doesn't follow if there's no event horizon, and so on. Unfortunately, event horizons are a really, really robust prediction of the theories of gravity that we use to describe black holes, so generally we're unwilling to accept that as a conclusion. So how about this one? What about black holes don't exist? Some authors have tried to argue that, in fact, if you look really carefully at the process of gravitational collapse, somehow just before you would form a black hole, the system kind of bounces and it doesn't form. Unfortunately, almost nobody believes their arguments, so that's also not a resolution. Now, another option is this one. So this was put forward as the inevitable conclusion by the people who debunked point number 1. They claimed that the only possible thing that could happen is when you tried to cross the event horizon, you would be zapped by arbitrarily large amounts of energy, completely incinerated, and that somehow this energy that zapped you would contain the information that's supposed to have been lost. This is actually a semi-serious proposal, and may well turn out to be true. There are a lot of extremely brilliant people kind of going back and forth, having a very childish, naysaying argument about whether this is plausible or not, and there doesn't seem any sign of a resolution coming up. So now for some of the really bonkers ones. Perhaps the theory of relativity, which is supposed to predict black holes in the first place, is wrong. Well, it could be, but it's got a lot of experimental evidence suggesting it's right, so it's going to have to be wrong in a pretty subtle way. And then an even more extreme version of the same idea, maybe quantum mechanics is wrong. There's even more evidence for quantum mechanics than there is for relativity, so this is even less likely, but it is still true that if the argument that led us to believe information can't be lost is false, then there's no paradox in saying that information is lost. So, I hope that kind of sums up how confused we are on the matter. I hope that you're still less confused than I am. And I think at this point we're willing to believe almost anything as long as it's backed up sufficiently, with perhaps 1 or 2 exceptions. And spoiler alert, sorry. And on that rather sobering note, I'll stop. Thank you.
Thanks, Andrew. Did anyone stay awake and follow that enough to ask a question? Chris?
On the idea of sort of, I don't know if you call them ghost particles appearing out of nowhere on either edge of the event horizon,
Yeah.
is it then not gaining equally the mass and information that it's radiating?
Yeah. So that's a good point. In the, I just run back to this. Here we go. Yeah. So you might say, well, hang on, why isn't this particle here carrying mass into the black hole? It turns out that whilst people will almost always tell you that having negative energy is impossible, in this context it's actually very possible. This particle mathematically can be said to carry negative energy. So it gives the black hole a negative amount of mass, or in other words, it takes mass away from it.
So that would be the particle and its antiparticle, is that right?
It's even more confusing than that. In the particles and antiparticles will usually both carry positive energy. This is very peculiar to the fact that there's an event horizon going on. I think the closest I've got to an intuitive explanation is that it's something to do with the binding energy of the particle with the black hole. But also I think I really don't know how to explain it intuitively. It's a subtle effect to do with quantum theory and curved spaces. Yeah.
Does the event horizon, or how does it interact with like quantum entanglement, for instance?
Yes. So that's an interesting point because in fact a lot of the arguments that demonstrate that the simple explanation in terms of correlations between the radiation and the stuff inside the black hole don't work is based around entanglement theory. So the idea is so these two particles should be in some sense maximally entangled with each other, and there are then various properties of quantum entanglement you can use to show that it would be inconsistent for all of the information to be somehow carried out in the radiation. So entanglement is a very important part of this phenomenon, yeah.
So am I right in that the sort of fundamental aspect of this problem is unification theory? You're trying to match what gravity is
Yes.
saying versus what quantum mechanics is saying.
Yeah.
And in that context, which sort of unification theory have you adopted in your work?
Okay, so I didn't want to bang on about unification theories because I did that at this conference last year. Yes, so the point is really that quantum mechanics and gravity do not play well together. Any naive attempt to put them into the same theory at the same time breaks in one or another ways, and this is kind of one of the most concrete manifestations we have of that fact. So the claim of the people who do these calculations, which I'm actually yet to be completely convinced by, is that you don't need to introduce a fully quantum theory of gravity. You should be able to sort of separate out the two aspects in the calculation. So you treat the black hole itself classically, and then you treat this evaporation as an effect of quantum theory living in a fixed background. What you should be doing is treating the background space quantum mechanically as well, and that's really hard to do. Some of the proposals involving absence of event horizons and things are based on string theory, which is sort of the only reasonably well put together idea of quantum gravity we have at the moment. There are other proposals, none of them seem to work. Or at least they might work, but they're also hard to calculate with, that nobody can actually make any progress. What we really need to resolve the paradox, I think, is a lot more solid calculations. We're very limited in what we can do at the moment. Yeah.
Go on, last question.
So thank you for that. I know approximately no relativity, but when the black hole is formed, I thought one argument was the information could be smeared around the edge of it. Is this the same as the fiery death?
Yeah, it's very closely connected to that. I think the people who proposed the fiery death scenario took it as a sort of manifestation of that idea. Yeah. So the idea, I think, is to claim that from the point of view of an external observer, actually you never, it's a little bit complicated, but you never actually quite see the black hole form for really complicated relativistic reasons. And so the claim is that, well, maybe the information is still there, sort of smeared on the horizon as it's forming. I think the issue with that is that the ability of black holes to evaporate completely means that even if you can save the information on the horizon, once the thing is gone, there is no horizon. So the information has to have gone somewhere, and I think people claim to have set the argument up precisely enough that you can rule that out as a resolution.
Right, very good. Thank you, Andrew.